Okay, last little video in this sequence. So now I want to talk about creating networks by yourself. Because before we did load an existing network dataset, we had like a matrix from this Florentine marriage dataset that I still have displayed here on the right hand side. But now let's start and generate a matrix just by ourselves. So the first thing I'm going to do is I'm generating a matrix. So that's what's going on here. It's generally, look at what's going on here. So it kind of, at the end, it's calling something M. Yeah, that's what the outcome of this command here is. It uses the matrix command to generate a matrix. Okay, now we have something in here, this one. And we don't really know what that is yet, but let's get to that back in a second. So apparently there must be some vector being the outcome of that command here. So it takes those values and then tries to turn them into a matrix with 5 rows and 5 columns. Let's unpack this command here a little bit, binom, and then I have like 3 numbers in there. So what do we get here? Well, basically we get a sequence of random numbers, yeah, drawn from a binomial distribution, meaning there's either 0 or 1. That's what this command does. It draws from a binomial, it draws random numbers from a binomial distribution, and it does that 25 times. Yeah, and then 1 is, let's look it up, that's probably the maximum that it kind of finds in here. So we have ibinom, n, size, and prop. So, okay, there we go. So it generates random numbers that have n number of observations, that's our 25. Then it kind of only does that size, what a size number of trials. We could do this a couple of times. Let's just show you for a second what's going on when you do that. So, okay, now I got like a 2 here, for example, right? So it kind of adds these things up, but I just want to have the 1 being the value. Okay, and then the last number corresponds to prop, and prop is the probability of success in each trial. Okay, so that means there's a 20% chance that a random number here is a 1. That's what it is. If I would bunk that, if I would go up with that number, 0.8 for example, you know, every time there would be an 80% time chance to have a 1 here. Well, if I would go to, let's say if I would go to 0 here, what are we going to get? Well, we're going to get just, there's a 0 chance to get a 1 in each trial. And there we go. But keep in mind that it doesn't mean that you always get the same number of 1s. So now I ran the command twice with a 10% chance to in each row. That's sort of how you can think of this, in each number that is being drawn. It's like randomly drawing a 1 or not with a 10% chance. And in this case, in this run, I had like only 1 times I kind of got a 1 as the outcome. While here I had, here's a 1, there's a 1, and there's a 1, right? So that's what you need to keep in mind. This is like a random draw. So it will be different every time you run the command again. Okay, so now coming back, now we know what this one here does. Let's run this here. So I get like 25 numbers, yeah, that go from 0 to 1, and each time there's a 20% chance that it is a 1. So I have 25 numbers, and that is essentially nothing else than a vector. You know, I could have assigned this I don't know, a name. I could have called it v. This is a vector, and if I would look at v, it is actually, you know, it's like a vector of the class integer. And here we go. So now I can use that in the matrix command and say, okay, well, turn this vector that you have here into a matrix that has 5 rows and 5 columns. Yeah, that's what this command does, and then save it in M. And you know, I could run this like that, or I could actually replace, let's copy that very quickly. I could replace this part here with B. Yeah, so it takes that vector. It takes that vector and turns it into matrix. There we go. Now I have something called M. And this is now this vector of 25 numbers turned into the matrix in exactly the same way as we dealt with it earlier. So it takes the first 5 numbers here and turns them into the first column. Then it takes the next 5 numbers and turns them into the second column. And then the next 5 numbers and turns them into the third column, and so on. And if I do that, if I run that now again, so, you know, if I take that out here, I will get a different matrix. Why? because I have a different row of random numbers here. There we go. Okay. So now I already have a matrix here. So now I can also change the diagonal of this. We don't really have to do that, but I just want to do it here anyway with the command diag of the matrix. What happens now? Now I turn all the diagonal values to value 99. If you kind of turn it into a network, it's going to ignore the diagonal anyway, unless you specify something here. It's self loop equals true, I think, something like this. Yeah, but you would have to look it up. Okay, so I now take this matrix M that I have, and I use the network command. Network together with a matrix, and then I want it to turn that into an undirected network and save that in G. And the way it turns it into an undirected network, let's look it up, because you see the matrix is not symmetric. There's a 0 here and there's 1 here. So let's see what happens. So now we have something called G, and it probably took a weak combination. There we go. So actually it turned that into, you see now it's symmetric. So it took whatever it found a 1 and kind of mirrored it on the other side, even though there was no 1 to begin with. So here there was no 1, but it kind of mirrored that. It basically, whenever there was at least one relationship from one I to another j, it also kind of it defined that to be an undirected relationship. Okay, so now we generate another new network. We can plot it. Poof, there we are. Another network generated. Okay, so now you've seen how we can create a network object from a matrix that either we loaded from somewhere else or that we generated ourselves. And now let's do something else, because you can also generate a network from what is called an adjacency list, an edge list. And remember, an adjacency list is another way of representing network data. Instead of having the whole matrix, it really has just two columns, one column being the sender and the other column being the receiver. It's like a different way of storing network information. And we can generate a network with that data as well. To do that, we would start, first of all, by generating an empty network. That's what this command here does. Network.initialize. Network.initialize generates an empty network. It lives in the network package. So if you type help package equals network, you find somewhere network initialize. And it generates an empty network with 5 nodes in it that should be undirected. Well, there aren't any relationships in it so far, but it will treat it as an undirected network no matter what comes afterwards. So I do that. There we go. So we have a new network. Let's look at the G. It's a new network with 5 nodes in it, but there are no edges. There's nothing in it. Yeah. So I could go and plot it. Let's plot it. You see my 5 nodes, but they are not really connected with each other at all. So now what you can do, now you can... Okay, so I started with a matrix and made a network out of that. So let's now do it in the other way around by first creating an empty network and then populating that matrix. And this is what this command does. So network initialize generates an empty network that has 5 nodes in it, and it sets it to be an undirected network. So we do that, run that command, and then I plot that, and I've already done that before. Here we go. So this is the outcome of it. So it's an empty network with 5 nodes in it. Okay. Now let's see if we can manipulate the underlying adjacency matrix. Well, G is for class network, right? But actually it's already clever enough that we can subset it as if it would be the adjacency matrix. Let's see, there we go. And now we can actually go to the first row and the second column of the adjacency of the underlying adjacency matrix and set that to the value 1. Right? Here, let's do that. And let's plot the network again. Here we go. You see, now we generated one tie from node number 1 to node number 2. Brilliant. We can actually go and set a whole row or a whole column of entries in the adjacency matrix to a certain value. And that's what we're doing here. So now I'm taking the second row in the adjacency matrix and comma, and then I leave it empty. That means like I address all of them, all of the columns in the adjacency matrix, and I set that to the value 1. And now what happened. Let me just quickly display this as a matrix G, because now you see it. You see now it actually took all the values of the second row in the adjacency matrix and kind of set it all to 1, except the diagonal. By default it reverts back to 0. And because we specified the network to be undirected, that's what we did over here, it also changed the second column, yeah, to mirror this row. And now we have a new network. Let's plot G, and poof, here we go. So we created our first star network. So the last thing about network generation that I want to talk about is generating networks from edge lists. And keep in mind that edge list is another way of storing data in a network. It's not like an n-by-n matrix. It's really just like a row, a column of the sender identification numbers and a column of the receiver identification numbers, like of an ego and an alter, a sender and a receiver, and their respective ID numbers. And there's an entry there when there's a tie from the sender to the receiver. And let's first generate an edge list, and then maybe you see what I mean by that. So this is now a command. It combines a couple of things. First of all, it generates a vector here. It generates a vector here, and these correspond to the entries in our sender column. This will correspond to the entry in our receiver column. These are two vectors that are being generated. And then we use the cbind command to combine these two vectors. And when you remember where you use cbind, we kind of take the first vector that we find, take that as a column, and the second vector that we find in the argument, take that as another column. And let me just run this line of code. So what it does, it generates something new called edge list. Let's look at it. Here we go. You see, so it took like 1, 2, 1, 1, 2 as the first column, and then it matched that with 3, 4, 5 as the second column. And we can interpret this now as an edge list of a hypothetical network, like a network where there's a relationship from number 1 to number 3, there's another relationship from 1 to 4, and there's another one from 2 to 5, right? Okay. So we could now use that edge list to change an underlying network. We first kind of generate an empty network here again to override that. So G is an empty network to begin with. There we go. It's an empty network. And then I subset it in a clever way. I use this edge list, which is, let's look at the class of it, because it is a matrix. So I can subset a whole matrix here and set this to 1. So what it essentially does, it kind of then uses this matrix as indices for where it should change values of the other matrix, of the underlying adjacency matrix of the network G. It's pretty clever. So let's do that. Let's run that. So now what happens, let's look up the S matrix G. See, now we got some values in here. And what we do have, for example, we have a 1 at the first row to the third column. So the first actor is connected to the third actor. 1 is connected with 3. And that corresponds to this pairing here. 1 is connected to 3. Or when we look at our adjacency list, or our edge list, this is the first entry. It's like 1 is connected to 3. The next one in our adjacency was 1 should be connected to 4. When you look into the matrix here, it's like 1, there we go, is connected to 4 indeed. There we go. Brilliant. And then the last one entry, the last tie we had in our edge list is from 2 to 5. We go to the second row to the fifth column. Now here's a 1 that corresponds to this value. Brilliant. So we have that. And because we specified the whole thing to be undirected, it automatically mirrored it onto the other side. Yeah, so there's this one corresponds to this one. This one corresponds to that one. This one corresponds to that one. And these are the 3 undirected ties we have in our network. And now we can plot that. There we go. I did something else. I changed the size of those vertices with vertex.cex equals to 5. And also I set the label so that you can see it. And here we have now our 3 ties that are specified in this tiny little edge list. From 1 to 3, there we go. From 1 to 4, and from 2 to 5. Okay, another thing you can do, you can also start with an empty matrix. And this is what I'm doing here. So I'm starting with an empty matrix of values 0, you know, and force that into a matrix with 5 rows and 5 columns. What does that do? You know, here we go. We have a matrix with only zeros. Call that M. And now I can subset things in this matrix again. So what does this here say, you know, like in the brackets? Basically, the first one is the row. So it goes to the third row in that matrix. And then it goes to a sequence of 4 to 5. So basically, it goes to the third row. Here we go, to the third row. And then it goes to the fourth and to the fifth column. And sets these two values to 1. Let's do it. Let's run it. There we go. So now we have a 1 here and a 1 there. So now you manipulated a matrix, set certain values to 1 that you wanted to be 1 to represent a tie, in this case from individual number 3 to individual 4 and from 3 to individual number 5. And now we can turn that into a network. Now I'm turning this into a directed network. You'll see the difference in a second. Just directed set to true. That's also the default. I generate a new object G, I override it, I plot it with this command and plot the labels. And here we go. So now we have 2 ties indeed for an individual number 3, 1 going to 4, you see the arrowhead here, and 1 going from 3 to 5, you see the arrowhead here as well, and no other relationships in there. Okay, so much about generating networks for now.